Resonance and formal charge. Some molecules have more than one valid Lewis structure. Let's look at ozone. So ozone is O3. So we've got 3 oxygen atoms, and they're going to be bonded to each other in some way. We're going to put them in a line here because we're not going to deal with any cyclic compounds in Chem 1A. That's for organic chemistry. So I've got 3 oxygen atoms. How many valence electrons will be in this molecule? 18. 3 times 6. So I've got 18 electrons. So I need to make bonds 2, 4, 6, 8, 10, 12, 14, 16, 18. Is everybody happy? No, the middle oxygen is not happy. What do we need to do? Double bond. They need to share some more. Okay, so which of these oxygens is going to do the sharing? Either. Yeah, just choose one. Okay, well, I'm going to choose the one on the left. So I'm going to take that one, and I'm going to make that a shared pair instead. Now is everybody happy? Yeah. But why did I choose the oxygen on the left? It was just random. What if we had the oxygen on the right do it?
They would be isomers.
Well, they're not isomers. What's an isomer? Yeah, you opened a whole can of worms. We're not talking about isomers right now. They're kind of like isotopes, but molecules. So, is everybody happy in this structure? Yeah. So, which one is correct? Both of them. And neither of them. Actually, neither of them is correct. But we can draw 2 valid Lewis structures. The only difference between these is where the double bond is. It's even between the same 2 elements. So how do we know what to do with this? This is a weakness of the Lewis model. It does not deal with this very well. When we study ozone, we observe that what you actually have is the average of those 2 structures. Each of these bonds is identical in an ozone molecule. You don't have one double bond and one single bond. We can tell the difference between double and single because the length is different. A single bond is longer and a double bond is shorter.
Couldn't you, if you just took that molecule and just spun it, it'd be the exact same?
Yeah, if you took this one and just rotated it in space, it would be the same as this one. But you would still have one short bond and one long bond. And when we study the ozone molecules, the bonds in them are identical in length. So what we do in the Lewis structure is we draw both of these and we put a double-headed arrow in between them. These are called resonance structures. The word resonance to me implies a back and forth, right? Like a guitar string vibrating, resonating. That implies that it's going back and forth between these, but that's not what it's doing. The actual structure is called a resonance hybrid. So here are those 2 Lewis structures that we drew, but actually it's a combination of them, and each of these bonds is really more like a 1.5 bond. The Lewis model does not have a way to draw 1.5 bonds. I mean, this is the best we can do with the dotted line, but then it becomes very difficult to stick the electrons in there, and that doesn't work out. And so we just take the 2 models that we can draw and we put a double-headed arrow in between them. This is like if you had a male German Shepherd and a female Golden Retriever, and they had puppies. The puppy is going to be a combination of those parent dogs. The puppy is going to look the same as itself all the time. It's not going to flash between looking like a shepherd and looking like a retriever, right? That's silly. But it's a combination of both. It isn't this one, it isn't that one, it's a combination. if you see pictures of my children, you'll see that they are a combination of my husband and myself. He is of Japanese descent, I am of Swedish descent, and the children are a mixture of that. And they all look like each other. So the problem with the Lewis model is that the electrons are localized. So the electrons represented in this bond are between those two particular oxygen atoms. And the lone pairs are on a particular atom. And that works okay for a lot of molecules, but some molecules have the electrons delocalized. They're kind of spread out and shared over the whole molecule or over a part of a molecule. And doing that causes a lowering of energy. That's called resonance stabilization. And we'll look at some models that deal with that much better in a little bit, in the next chapter. Any questions?
What is delocalized?
Delocalized means that it's not localized. So localized means it's specific to a particular place. So like this double bond, the electrons in the second bond there in the Lewis model are between these two oxygen atoms. But actually, the electrons in that second bond are spread out over the whole molecule. They're delocalized. They're not in a specific location.
So if you put those two together?
Yeah, these are our poor representations of what actually is. Okay, so neither of these actually exists in nature.
What would be the correct way to write it? The end product?
So the correct way to write this would be to, in the Lewis model, is to draw both of these and put a double-headed arrow in between.
Why not just write the?
Why not just write this? If we write this and then put the lone pairs in, we end up with a poor representation of the lone pairs because it shows that some of the electrons are not paired, and in actuality they are paired. And so that doesn't work very well either. So this is what they've decided, and we just have to go along with them. So you draw all the possible resonance structures. There can be more than two. And you put double-headed arrows in between. And then we understand that it's an average of those. Yes?
So the reason it's bent, the molecule, is because of that little heat thing, which causes it to be more negative?
We'll get to shape, but the reason they're showing this as not a straight line of three balls is because there is a lone pair on the central atom. And so it's more of a trigonal, well, it's a bent shape because of that. We'll get to that in the next chapter. In this case, the two resonance structures are essentially identical. Like someone pointed out, if we take this one and just rotate it, we get that one. They're identical. And so these are going to contribute equally to the hybrid. We know from genetics in animals and in people that sometimes one of the parents has a much stronger influence on the outcome, on what the children look like. You look at my kids and you see that my husband had much more influence on their appearance than I did. They all have brown hair and dark brown eyes, and they look at the sun in the spring and they turn a beautiful golden brown. That's all from my husband. They did get some things from me, but he had more influence on their genetic makeup than I did. And so we'll see that also with different resonance structures. Sometimes they're not identical like these are, and one will have more influence than another. Let's practice and write a Lewis structure for the NO2 minus ion. It says include resonance structures. That says there are resonance structures and we have to include them. If you're doing resonance structures, you have to do all the resonance structures. Well, let's start out by just doing a structure. NO2. How are we going to arrange those three atoms?
Nitrogen as the center.
We'll put nitrogen in the center. One of the guidelines was put more electronegative atoms on the outside terminal. So if we put nitrogen in the middle and oxygens on either side, the oxygen is terminal, it only has one connection. The nitrogen has two connections, it's not a terminal atom. And then we have to figure out, well, how many electrons do we have to mess around with? We have two oxygens, they each have 6 valence electrons. We have one nitrogen with 5 valence electrons. And then the negative does what? You add one. Sometimes that gets confusing. The -1 means you add 1. So 2 times 6 plus 5 plus 1, I think, is 18. 18 valence electrons. We have to start out by putting in some single bonds. 2, 4, 6, 8, 10, 12, 14, 16, 18. Is everybody happy? Nope. We ran out of electrons, we need to make a multiple bond. Well, I'm going to make this one on the left share. So if that oxygen shares an extra pair of electrons with the nitrogen, now we have satisfied the octet rule. We're not quite finished here because this is an ion, and so we need to put brackets around it and indicate the charge. This is very similar to the ozone molecule, isn't it? Yeah. So we just kind of arbitrarily chose to make this oxygen share, but we could also make that oxygen share instead. And so the other resonance structure would have the double bond on the right instead. Negative charge, and then double-headed arrow between them. The actual structure is an average of those. Any questions? Yes?
Put the negative charge outside.
We put the negative charge outside of brackets. It's convention. I like to think up reasons for things, even if they aren't the actual reason. It helps me to remember if I can think of a reason that makes sense to me. The reason that makes sense to me is with all these dots around, a minus sign could get lost in this structure, and so whenever we put a charge on an ion or a molecule, well, molecules don't have charges, on an ion that has some lone pairs or anything on it, we always use the brackets. Mastering chemistry can't do brackets. Any other questions?
In that case, you apply the charge in the nitrogen or the oxygen?
We'll get to that when we talk about the formal charges. As to, if you don't have the brackets on mastering chemistry, what do you do with the charge? We'll get to that. You had a question?
Like LIGO and dextrose, is that only used in organic chemistry?
The LIVO and dextro is organic chemistry, yeah. No. That has to do with chirality and optical activity, and these compounds are not optically active. So, formal charge. Sometimes we can draw different Lewis structures that satisfy the octet rule, and we're not sure which one is the best one. And so formal charges help us to figure this out. This is a made-up thing. This is just a trick that we use to help us predict correct structures. The formal charge is a fictitious charge. These things that we're doing are molecular compounds or ionic polyatomic ions with covalent bonds. We're not saying that the atoms involved have charges, but this is just to help us figure out what's going on. So the formal charge is the charge it would have if all the bonding electrons were shared equally between the bonded atoms. We calculate it completely ignoring electronegativity. Your book explains it as the difference between the number of valence electrons that an atom has by itself and the number of electrons that it owns in the Lewis structure. And they give you this equation, which I think is horribly confusing. Use it if you like it. I'm going to ignore it. So some rules for formal charges. The sum of all the formal charges in a neutral molecule must be 0. If it doesn't come up 0, you're doing something wrong. The sum of the formal charges in an ion is going to equal the charge of the ion. If it doesn't, you did it wrong. We want small or 0 formal charges. Those are preferable. So when we have different structures and we're comparing the formal charges, we're going to pick the one that has smaller magnitude of formal charges. We'd like them to be 0. Sometimes you have to have formal charges. And then we want the negative formal charge to be on the most electronegative atom, because that atom is more attractive to the electrons. The formal charge is saying if you have a negative formal charge, it's like, okay, there's kind of an extra bit of electron density on this atom. That needs to be the more electronegative. Okay, so let's look at this example. I'm going to draw these Lewis structures down here because they're awfully tiny in there, and I want to be able to write on them. So, 2 different structures for HCN. We're trying to figure out the best skeletal structure. How are the atoms arranged? These are not resonance structures. How the atoms are connected is different. This is H with, C in the middle, N, and this one has N in the middle. So this is not just a moving around of a double bond or something. This is a completely different type of molecule. So we're going to pick the best one by looking at formal charges. So doing formal charges is a little bit like you're taking this molecule and all the atoms are getting divorced, right? And they're just going to split all the shared stuff equally. So I'm going to draw a line here and here. All the bonds are just going to get cut in half. Each bond is 2 electrons. And so we look at this hydrogen. If we cut this all up, if we divorce the atoms, the hydrogen has 1 electron. This carbon has 1, 2, 3, 4 electrons. The nitrogen has 1, 2, 3 from the bonds and 2 from its lone pair. I think that makes more sense than the stupid equation. So in calculating the formal charge, what we're going to look at is we're going to look at the number of valence electrons that element has and subtract the number of electrons that the element would get in the divorce of the molecule. So for hydrogen, how many valence electrons does hydrogen have? 1. And in this broken up molecule, how many electrons does it have? 1. Okay. So each of these bonds is 2 electrons, right? And when we split the bond, when we cut it, they get divided equally. So this isn't shared anymore, we broke it. So the hydrogen has 1 on its side of the line. So 1 minus 1 is what? 0. The formal charge on this hydrogen is 0. Let's look at the carbon. How many valence electrons does carbon have? 4. How many does it get in the breakup of this molecule? 4. So that's 0. It gets this one, 1, 2, 3, 4. Everybody see that? How many valence electrons does a nitrogen atom have? 5. And how many does it get in the breakup of the molecule?
5.
We've got to count these 2. So a total of 5. So each of these atoms has a formal charge of 0. That's good. Let's do this other one. So again, we're just cutting all the bonds in half. Yeah, this one's different. I'll put those dots in there to help us see. So hydrogens have one valence electron. How many does it get in the breakup? 1. And so 1 minus 1 is 0. Nitrogen atoms have 5 valence electrons. How many does this nitrogen get in the breakup? 4. 5 minus 4 is plus 1. Carbon atoms have 4 valence electrons. How many does this carbon get in the breakup? 5. So 4 minus 5 is negative 1. So these formal charges, 0, plus 1, and minus 1, add up to 0. These formal charges also did. All the formal charges have to add up to the overall charge on whatever it is. This is a molecule, they have to add up to 0. This is not as good of a structure because we have non-zero formal charges. This one is better because all the formal charges are 0. If we were comparing this to something else that also had formal charges, this wouldn't be as good because here we have a positive formal charge on nitrogen, a negative formal charge on carbon. Which is more electronegative, carbon or nitrogen? Which is closer to fluorine? Nitrogen. And so this is not a happy situation. If we have to have these formal charges, then nitrogen should have the negative one. So this is the best structure.
What is the point of this? Just to figure out what is the better structure to use?
The point is to figure out, to help us decide between multiple skeletal structures, but also in looking at different resonance structures, we can tell that some of them have a larger contribution to the actual resonance hybrid than others do. I want to show you something else that can help in figuring out what's a good molecule, how to put these things together. Let's look at carbon, nitrogen, and oxygen. Let's throw fluorine in there as well. So how many valence electrons does carbon have? 4. 1, 2, 3, 4. How many of those are not paired? All 4 of them, right? Carbon likes to form 4 bonds. Carbon makes 4 bonds. How many valence electrons does nitrogen have? 5. 1, 2, 3, 4, 5. How many are not paired? 3. Nitrogen likes to make 3 bonds. How many valence electrons does oxygen have? 6. 1, 2, 3, 4, 5, 6. How many unpaired? Guess how many bonds oxygen likes to make? 2. This is getting boring. Fluorine has 7. 1 of them is not paired. Fluorine likes to form 1 bond. If this pattern is followed, those atoms will have a 0 formal charge. How many bonds is this carbon making? 4. Its formal charge is 0. How many bonds is this nitrogen making? 3. 0 formal charge. Here, the nitrogen has 4 bonds. It ends up with a formal charge. Here, the carbon has 3 bonds. It ends up with a formal charge. Any questions? It's kind of a shortcut thing your book doesn't really mention.
Sorry, so back to the 5 minus 5 with the nitrogen on the left. Where did you get the second?
So this 5 is the number of valence electrons that nitrogen has. This is the number of electrons that nitrogen would get when we break up the molecule by cutting all the bonds in half. So we're cutting these bonds in half, so there's 3 electrons from that triple bond plus the lone pair. 5 electrons. Any other questions? Let's do an example. Assign formal charges to each atom in the 3 resonance forms of N2O. They're telling us how many resonance forms. They're also saying nitrogen is central. So we need to put nitrogen in the middle and then figure out 3 different ways to draw this. And then the question is, which resonance form is likely to contribute most to the correct structure? We can only do that with formal charges. Okay, well, we need to put nitrogen in the middle. So we're going to have nitrogen on one side and oxygen on the other side. And then, so the order of the atoms, the skeletal structures is not going to change. I'm going to draw all those guys out. How many electrons, how many valence electrons? 2 times 5 plus 6 is 16. So 16 electrons. So I have to put single bonds. There's 2, 4, 6, 8, 10, 12, 14, 16. We need multiple bonds. Well, this nitrogen's happy, so we're going to make him share. Now, both of the nitrogens are happy, the oxygen isn't happy. So we could make this middle nitrogen share. This guy can't share because that just wouldn't work. So I'm going to take this lone pair and make it into a double bond. Does that satisfy the octet rule? Everybody have 8 valence electrons? Yeah, it does. So how else could we draw this? We have a double bond on each side. How about a triple and a single? So we could put a single bond here and a triple bond there. So then there'd be a lone pair here. And I've got 4 lone pairs over here and a total of 4 bonds. I've got 4 lone pairs and 4 bonds. That's going to work out okay. And then the other option is, instead of putting the triple bond between nitrogen and oxygen, we'll put it between the 2 nitrogen atoms. And to indicate these are resonance, I didn't leave much room for my arrows, but we would draw the double-headed arrows in between. Everybody okay with that? So we could look at this and do the bond counting thing and say, well, here we've got nitrogen with 2 bonds. This one has 4 bonds, and oxygen has 2 bonds. That's what oxygen likes, but neither of these nitrogens has 3. Here we've got a nitrogen with 4, a nitrogen with 1, an oxygen with 3. That's not real great for anybody. Here we've got this nitrogen with 3, that nitrogen with 4, and oxygen only 1. So we can't just use the preferred number of bonds to identify which of these is more stable. So we have to look at formal charges. So we're going to break up, imagine breaking up these molecules. How many valence electrons does nitrogen have by itself? 5. How many does it get in the breakup? 6. So 5 minus 6, its formal charge here is -1. Here's another nitrogen. 5 valence electrons minus how many does it own? 4. So that's +1. And how about this oxygen? 6 minus 6. So this one's 0. So the formal charge on this nitrogen is -1. On this nitrogen, it's +1. And on the oxygen, it's 0. Over here, this nitrogen, we start with 5 and subtract how many? 7. So that's a formal charge of -2. How about the one in the middle? 5 minus 4 plus 1. And the oxygen is 6 minus 5. So that's +1. This oxygen would get 1, 2, 3, 4, 5 electrons if we just chopped all the bonds. So which is a better combination of formal charges? -1 + 1 and 0, or -2 + 1 and +1? The first one, these are lower. One of them's actually 0. These formal charges are higher, so this is not the best one. Then we have to do it again over here. Cut the bonds. This nitrogens have 5 valence electrons. How many does it get in the breakup? 5. Here's another nitrogen. 5 minus 4. So this is +1. And oxygen is 6 minus 7. So this is a formal charge of -1.
So the third one's better because the negative charge is on the oxygen.
Yep, this one is better than that one because here we have the negative formal charge on nitrogen. Here we have the negative formal charge on oxygen. Oxygen is more electronegative than nitrogen. It's closer to fluorine on the periodic table. Any questions? This is one of those things that once you do it a couple of times, it's really not that hard. Just think, okay, we're chopping all the bonds in half, and what does everybody get to take home? Compare that with what they started with, and that's the formal charge. Okay, let's do this one. Draw the Lewis structure, including resonance structures for diazomethane, CH2N2, and it says that carbon is central. For each resonance structure, assign formal charges to all atoms that have formal charge. Because it gets a little tedious with all the little numbers writing in, if an atom does not have a formal charge, if its formal charge is 0, often we'll just not write anything, and we'll just write the ones that have a positive or negative formal charge. Okay, so carbon is central. Okay, we can do that. Put carbon in the middle. And then what should we do? Put the 2 hydrogens and the 2 nitrogens on the carbon. So we'll put hydrogen and hydrogen and nitrogen and nitrogen. And how many valence electrons are in this molecule? Whoops. 2 for each of the hydrogens, and 4 for the carbon, and 2 times 5, so 16. Start by putting in some bonds. 2, 4, 6, 8, 10, 12, 14, 16. The hydrogens are happy, the carbons are happy, the nitrogens are not. We ran out of dots, that means we need to make multiple bonds. Can we make multiple bonds? Why not? Because then carbon's already full. Carbon's already got an octet. It can't share anymore. If we put one of these lone pairs in here, then carbon's going to have 10, and that's not good.
You attach a hydrogen to a hydrogen.
We can't attach a hydrogen to a hydrogen because hydrogen can only form one bond. We're going to have to rearrange something, right? So we could take this nitrogen and stick it over here, or we could take this hydrogen and stick it on a nitrogen. So let's try doing that. Just move this guy. So I didn't change the number of electrons, I just changed the arrangement a bit. Now I could take this lone pair and stick it in there. So this nitrogen's good, carbon's good. What about this nitrogen?
Wait, wouldn't you want to do that double bond on the bottom nitrogen, not the one on the right? You could do them both.
Well, I could do that, but I'm going to have the same problem. This nitrogen's happy, that one isn't.
How do we switch the nitrogen to hydrogen?
So we need to put this hydrogen on the nitrogen. So we stick this down here. Now this nitrogen's happy, right? 1, 2, 3, 4. 2468. This one's happy, that's, the hydrogens are happy. Hydrogen is so easy to satisfy. One bond, it's good. Carbon's not happy, but now we can take that lone pair and make it a double bond. So because of how we arrived at that, it ended up being a little messy. So I'm just going to copy it over here. Now it says include resonance structures.
Ouch.
Ouch.
indeed.
Okay, doesn't this look like the ozone? Well, actually not the ozone, but doesn't this look like the last one we did with the N2O, where we had two double bonds and then we tried a single bond on one side and a triple bond on the other side? So we could do that. So let's try a triple bond over here and a single bond over there. That works with the octet rule, but then we should also try it the other way. Good? Okay, so we've got three different structures. They're not exactly the same, right? The top one and the bottom one are essentially the same, just rotated, right? But this nitrogen is a different atom than that one, and so this is a resonance structure, these two. But this one in the middle is different because the bonds are designated differently. So let's look at formal charges. Let's do the one on the top. Cutting all the bonds. You can actually just ignore hydrogen. Hydrogen has one valence electron, it always makes one bond, and so its formal charge is always going to be 0. So all the hydrogens are good. This nitrogen has 5 valence electrons. How many does it get in the breakup? 4. 5 minus 4 is +1. So that has a +1 formal charge. Carbon has 4 valence electrons, and in the breakup of this molecule, it would get how many? 4. So that would be 4 minus 4 is 0. So I'm not going to write anything. This nitrogen, 5 minus how many? 6. So this would be -1, and then the hydrogen's going to be 0. So here we have a positive and a negative formal charge. We don't really have to go through the whole thing to do the one on the bottom. The one that has the lone pairs and the 2 single bonds has a formal charge of -1, and the other nitrogen is the +1. Everybody okay with that? But the one in the middle is different. So this nitrogens have 5 valence electrons. How many does it get in the breakup of the molecule? 3 and 5. It gets 5. It has 3 from the breakup of the bonds, plus 2 for the lone pair. So 5 minus 5 is 0. I'm just going to write the 0 there for emphasis. How about this carbon? 0. It has 4 valence electrons. It would get 4 in the breakup. It comes out neutral. This nitrogen, also 0. So which is the most stable? The one in the middle. And yeah, I'll just stop there. Any questions? Mm-hmm.
Could you always just use that method where you just see how many bonds it wants to form and just diffuse it with that without doing formal charges?
If it follows the octet rule, yes.
And if it doesn't, you have to do formal.
Yeah, if it doesn't, then you have to look at formal charges. So the question is, can you just look at the number of bonds and that little trick I showed you? Yeah, you can. So nitrogen here having 4 bonds, that tells me it's going to have a formal charge. This one where nitrogen has 3 bonds, carbon has 4 bonds, nitrogen has 3 bonds. Everybody has the number of bonds that they prefer, and so all the formal charges are going to be 0. Any other questions?